The pressure P in kilopascals and volume V in liters and temperature T in kelvins of a mole of an ideal gas are related by the equation PV equals 8.31 times T. We're asked to find the rate at which the volume is changing when the temperature is 315 kelvins and increasing at a rate of 0.05 kelvins per second, and the pressure is 17 kilopascals and increasing at a rate of 0.02 kilopascals per second. Let's begin by stating all the given information. We know the temperature T equals 315 kelvins. We know the temperature is increasing at a rate of 0.05 kelvins per second, which means the derivative of big T with respect to time t is equal to positive 0.05 kelvins per second. We know the pressure is 17 kilopascals, so P equals 17 kilopascals. And finally, the pressure is increasing at a rate of 0.02 kilopascals, which means dP dt equals 0.02 kilopascals per second. So all this information is given, and now we're trying to find the rate at which the volume is changing, and we're given the equation PV equals 8.31 times T. So because we're looking for the rate at which the volume is changing, we want to determine dV dt. So let's first solve this equation for V by dividing both sides by P. So we can say that V equals 8.31 times T divided by P, or if we want, 8.31 T times P raised to the power of negative 1. And because V is a function of big T and P, we'll have to apply the chain rule given here below. So let's go ahead and write out the chain rule using our variables. So we'll have the derivative of V with respect to T is equal to the partial derivative of V with respect to big T times the derivative of big T with respect to time, or T, plus, well, the partial derivative of V with respect to P times dP dt. Now let's find our partial derivatives. So we have dV dt equals the partial derivative of V with respect to T, so we'll differentiate with respect to T, treating P as a constant, which would just give us 8.31 times P raised to the power of negative 1, because the derivative of T with respect to T would just be 1. So we have 8.31 times P to the negative 1 times we have dt dt, which we know the value of, but we'll substitute that value in the next step. And then we have plus the partial derivative of V with respect to P. So we'll differentiate with respect to P, treating T as a constant. So we're going to multiply by negative 1 and then subtract 1 from the exponent on P. So we'll have negative 8.31 T times P raised to the power of negative 2. So we have negative 8.31 times T times P raised to the power of negative 2 times dP dt. Notice how here we can write this as a difference rather than plus a negative. Let's continue on the next slide. Before we perform substitution, let's rewrite these negative exponents as positive exponents. So we'd have dV dt equals, here we'd have 8.31 divided by p to the first, or just p, times dt dt minus 8.31t divided by p squared times dp dt. And now we'll substitute the given values in for t, dt dt, p, and dp dt. So we have 8.31 divided by p, which is 17, times dt dt, which we know is 0.05. And then we have minus 8.31 times t, which is 315, divided by p squared, which would be 17 squared, times dP dt, which is 0.02. To save some time, I've already determined these values. This value here is approximately 0.02444 minus This value here is approximately 0.18115. So if we find this difference around to 4 decimal places, we would have dV dt is approximately negative 0.1567. Now this is measuring the change in the volume with respect to time. And going back to the question just for a moment, notice how the volume is in liters and our time is in seconds, which means the units here would be liters per second. So the volume is decreasing at 0.1567 liters per second when we have all of this given information. I hope you found this helpful.